Sorry, my video team, I forgot all about you. Okay, now draw theta equals pi over 4. Draw the line theta equals pi over 4, as r is allowed to run anywhere it wants to go. Okay, what was the first thing I told you to do? What was the first thing I told you to do?
X equals 2.
X equals 2. So here's x equals 2. No matter what y is, x is 2. So I get that coordinate curve, my Cartesian coordinate curve x equals 2. What's the next thing I told you to do?
Y equals 4.
Y equals 4.
So y is always 4. Y is always 4. X does whatever it wants. And I get this coordinate curve. Okay, then I told you to draw the coordinate curve in polar coordinates of r equal to what? Of r equal to what? I completely forgot.
R equals 2.
R equals 2. So here's r equals 2. You're out a radius from the origin 2, and theta is allowed to do whatever it wants. Well, what's going to happen if you hold a radius of 2 and theta does whatever it wants? What are you going to get? A circle, and it's just going to keep going around in one direction or another. Now, what was the last thing I asked you to do? Draw.
It equals pi. Yeah.
So you take an angle from here up pi over 4, and r is allowed to run however it wants between minus infinity to infinity, and this is the coordinate curve theta equals pi over 4. Okay, I've got a sector of an annulus. You know, like Dr. Warren, what the hell's an annulus? Think of a tire. Think of a tire as an annulus. It's the inside between two circles, and I'm taking a piece of it. Now, r is running between a and b. My radial variable is running between a and b. r equals a is this circle. R equals b, theta is allowed to do whatever it wants, is this circle. Theta is running between alpha and beta. Theta equals alpha, r is running like this. Theta equals beta, r is running like this. Write down the double integral. Write down the form of the double integral. If you were integrating a space sheet of z equals f of r and theta over that sector of that annulus. Write down the double integral based off our videos that would represent the volume underneath f of r and theta down to that domain D. Now again, on Monday, you're going to have your videos on. On Monday, you have to have your videos on. All right, go to grid view, go to grid view, go to grid view, go to grid view. Hold up what you've got for this old man. Hold up what you got for this 60-year-old man here. Gordon, I like it. Gordon, I like it. Caitlin, I can't quite see yours yet. Oh, I don't think I'm getting enough light. Luke, I like what you got. Rhett, I'm not seeing anything. Cosmo, you're missing the R, Cosmo. You're missing the R in the differential. You're missing the R. What do you got there? Rachel. Excellent, Rachel. Excellent, excellent. Okay. Jake, what do you got for me there? Let me see, Jake. Jake, you're missing the R also. You're missing the R also. Okay. How many people had a double integral? How many people had a double integral? I mean, we're in a section called multiple integrals. How many people? Okay, the outer integral is the integral with respect to theta. The outer integral is the integral with respect to theta. What's theta running between? What angles is theta running between? Alpha and beta. I'm running between the coordinate curve, theta equals alpha and theta equals beta. Now my radial variable's running between r equals, the curve r equals
A and B.
A and B. My space sheet. And then there's the differentials. dx dy becomes r, and this is what was missing. This is what was missing in a lot of people's. dr d theta. And people are like, Dr. Warren, why is there a stinking r? Why is there a stinking r there? So ask me that. Ask me that.
Why is there an R there?
Oh, go watch video 2. Go watch video 2 is my answer. Go watch video 2 if you want to know why there's an R there. Okay, how many people are feeling like, okay, I at least can write that down? How many people are at least like I can write that down? Okay, this is called flipped classroom. I've never done a flipped classroom, ever. I've never done a flipped classroom. I know there are other departments and there are my colleagues that do flipped classroom. So I told my professors, my colleagues this year, my professors, that I was flipping my classroom all semester long, okay? And I think this is funny, but they didn't think it was so funny. I'm like, I flipped all the chairs that were facing towards the front of the room, towards the back of the room, okay? And now I teach in the back room. I'm doing a flipped classroom. They're like, you're still lecturing though. And I'm like, yeah, I'm still lecturing. They're like, well, that's not flipped classroom. If it's flipped classroom, you put videos up, they watch that, and then you use the classroom to do homework. Okay, so now we're actually going to do a real flipped classroom, kind of. Okay, I'm going to work one example, and then you guys are going to try to do an example from your homework. The homework that I assigned in section 15.3 was what problems? You have a quest coming up. Just reminding you. You have a quest. What homework problems did I assign in 15.3? Because you're going to be busy doing these today. Go to Canvas.
Questions 9, 11, 19, 29, and 31.
9, 11,
19,
19,
29,
29,
and 31.
31. Okay, so each one of these problems could take 10 to 15 minutes. Each one of these problems could take 10 to 15 minutes, okay, to actually do. So let's go 15. 1, 2, 3, 4, 5. Okay, that would be an hour and 15 minutes. We've already spent 15 minutes. Are we going to be able to do all your homework? Are we going to be able to do all your homework? And the answer is no. So now I'm just going to work an example. Let me work problem number 7. Let me work problem number 7, which should help you on problem number 9. Okay, so I'm going to read problem 7 to you, and you're going to be glad I'm not your dad, that you didn't have to hear this voice read Dr. Seuss to you as a child. You have a double integral with a d underneath it, so write that down. You got a double integral with a d underneath it. Here's the space sheet, x squared y. Okay, now they're explaining who d is. Where d is the top half of the disk with center at the origin of radius 5. Read that again, Dr. Warren. Where d is the top half of the disk with the center at the origin of radius 5. Try to draw the d. Give yourself an xy and try to draw the d. What do you think they're talking about in problem 7? the top half of a disk whose center is at the origin and whose radius is 5. Okay, go to grid view and show me what you've drawn. Go to grid view and show me what you've drawn. Let me see in this homework activity what you guys have for me. Good, Caitlin, good, Caitlin. Gordon, did you shade anything? Did you shade anything? Where's your top half? Nice, Emily, nice, Emily. Nice, Jay. Good, Luke. You guys are doing great. You guys are doing great. You guys are doing great. Okay, almost everybody drew something like that. How many people got that? How many people got that as far as what we have? This is what we're going to be integrating over. Now, what's the radius? What's the radius of this circle? What's the radius of this circle? And I hear nothing coming back from the room. What's the radius of the circle? 5. Okay, now let's go over here and look at our base diagram for polar coordinates. I need some domain for r, which will work into an a and a b, and I need some angle alpha and beta. I need some angle alpha and beta for my theta. Try to find to the best of your ability what you think r is running between in polar coordinates. Who's your a's and who's your b, and who's your theta for your angular variable in polar coordinates. That would create that disk if you were going in polar coordinates. Okay, guys, now you help me out. What do you think what is R running between? What values is R running between if I'm trying to get this disk?
0 and 5.
Between 0 and 5. It's starting at 0 and running to 5. So we at least have that. What angular variable, if I'm sweeping like this, what is the angular variable running to? R is running between 0 and 5. What's theta running between? What's the angular variable running between?
0 and pi.
0 and pi. It's running between 0 and pi. So keep the x squared y right now the same. Write down the double integral. It's kind of asking you to do the same thing I was asking before. Write down the double integral that would represent that volume if we could figure it out. If we could evaluate the following double integral in polar coordinates, what would that integral be? This is flipped classroom. You're doing the work. Okay, go to grid view, go to grid view, go to grid view, go to grid view. I'm not writing down anything. This is flipped classroom. Go to grid view. Hold up what you have so others can see. Hold up what you have so others can see. Luke, I love how dark that is there. That's awesome. You could have that. So look at what others have. Look at what others have. So Gordon, you didn't go. I need your polar dx differentials. But I like what you have there. Jake, I like what's there. But Jake, who is the space sheet? Who is the space sheet? Stuart, you're missing oh wait, maybe you're not. Stuart, do you have an R in there? I just can't see. Is there an R in the dr d theta? You need an R. You need your R there, that dreaded second video. You need the R dr d theta. R dr d theta. Let me see, Raylan, what you got there for me. Awesome, Raylan. Awesome, awesome. Okay, now Dr. Warren's going to catch up. Dr. Warren's going to catch up. Theta's running between where and where? Theta's running between where and where? Help Dr. Warren out. What is it? What is it? What is it?
0 to pi.
0 to pi. R's running between 0 and 5. And then we got our space sheet. Then what will most, guys, if I had a dollar for every time somebody forgot the R, I would be in Vegas right now, not stuck in Burris 126 on a cold day in Virginia, okay? The differential is not dx dy, but it's r dr d theta. You're like, Dr. Warren, why is there an R? Watch the second video. Watch the second video. Okay, now right now, this is a confused little integral. This is a confused little integral. It doesn't know if it wants to be Cartesian or polar. It doesn't know if it wants to be Cartesian or polar. It wants to be polar. So now change that space sheet into its polar form. Change that space sheet into its polar form. Okay, where I see the x, I'm going to put a what, guys? Where I see an x, I'm going to put a what? Where I see the x, I'm going to put a what?
R cosine theta.
So I'm going to have an r squared cosine squared theta. How many people went there with me? How many people have that or had that? Where I see the y, I'm going to put a, where I see the y, I'm going to put a r sine theta. I still got this r for my differential hanging there, dr d theta. Okay, guys, look at the inner integral. For the inner integral, are we integrating first with respect to r or with respect to theta? Are we integrating with respect to r or with respect to theta? R. So what can you pull out of that inner integral? What can you pull out of that inner integral? Anything with the theta. So I want you to now go ahead and do that. Pull out those functions of theta and then do the integral with respect to r. It's homework. Well, it's not really homework. It's like homework. Okay, how many people got to here? How many people got to here? How many people got r to the 5th over 5? How many people got r to the... Okay, what does the line mean? 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 Plug that dude in and plug that dude in. When you plug 5 in, you're going to get 5 to the 5th over 5. which is 5 to the 4th. And so then you're just left with 5 to the 4th. Pull that all the way out. The integral from 0 to pi and now you just have that other one-dimensional integral to use. You have to integrate from 0 to pi cosine squared sine. What integration technique are you going to use? What integration technique are you going to use to try to do that integral? What integration technique, guys?
Integration by parts.
You could use integration by parts, Gordon. I think that would probably make it maybe even a little bit harder. There's an easier one that you guys can use to actually try to do this.
U sub.
U sub. Who would you let u be equal to? Who would you let u be equal to?
Cosine squared.
Cosine theta. So try to do that u sub. Listen to me. Listen closely. Change your limits of integration. Don't make Dr. Warren angry. Change your limits of integration when you do your u sub. So you go ahead. Try to do the u sub. One of your classmates said u equals cosine. Okay, guys, I'm going to try to catch up, and for sake of time, we're going to end this thing. If u is equal to cosine, then du would be equal to what? If u is equal to cosine, then who was your du?
Negative sine.
Very good. Negative sine theta. I want the d theta. You got to have your d theta there. Now look at your integral. We're set up really well. This is u squared. This is u squared. But I don't have a minus there. I don't have a minus there. But I can remedy that by putting a minus here and balancing it out by putting a minus there. Change your limits of integration. When theta's zero, u would be the cosine of 0. Which would mean u would be equal to, which would mean u is equal to 1. But when theta's pi, u would be the cosine of pi, which is negative 1. So we're trading this integral. We're trading this integral for minus 5 to the 4th the integral from -1 to -1, this ended up being 1, this ended up being -1 of u squared du. Now this integral's jacked because b is actually less than a. B is actually less. It's not proper. This is not written in a proper way. It's not an improper integral like we think of improper integrals from Calc 2. It's just not right. If I make it right by flipping the limits, what do I have to do with the sign out there? If I flip it, what do I have to do with the sign out there?
Turn positive.
Turn it positive, turn it positive. How many people are pretty comfortable they can do the rest of this problem? How many people could do the rest of this problem? It doesn't seem like it's worth investing class time when you don't know how to do polar integration to do those. Agree or disagree? Agree or disagree? Okay, so now let's do one of your homework problems. We've got 9, 11, 19, 29, and 31. Why don't you guys try to do problem number 11? And I'll read 11 to you. Okay, on number 11, you got a double integral and a d. You got a double integral and a d down below. The space sheet is e raised to, all of this is in the exponent, minus x squared minus y squared. E raised to the minus x squared minus y squared. And here's the thing. Then you got a dA. So I guess I'll just switch this up a little bit for us. And this is what they're telling us about where D is the region bounded by the semicircle x equals the square root of 4 minus y squared. The semicircle x equals the square root of 4 minus y squared and the y-axis. So it's the region between the semicircle described by x equals 4 minus y squared and the y-axis. Try to find what the domain looks like. Try to find what the D here that you're actually integrating over looks like. Bounded by x equals 4 minus y squared and the y-axis. How many people think they have it? How many people think they have D? Does anybody think they have D? Cosmo thinks he has D. Does anybody else think they have D? Okay, show me what you have. Let me see what you guys have for D. Cosmo, you're right. Gordon, you got it. Caitlin, you got it. David, that's right. Okay, so let's at least get everybody caught up with this. Whenever you see this, guys, and you're trying to deal with it in polar coordinates, square both sides. And when you square both sides, you're going to get x squared equals 4 minus y squared, which implies x squared plus y squared equals 4. So you got a circle You got a circle of radius what? You got a circle of radius what? Not 4, but 2. So you got a circle of radius 2. It's x equals, so you're talking about functions this way or that way. It's the positive part. So you're taking that, and you're going between that and the y-axis. And here's your y-axis. Does that domain look good for polar coordinates? Does that domain look good for polar coordinates? Try to find the range for r and the range for theta and write down a double integral. Write down a double integral in polar coordinates that would find the volume. Don't worry about the x and y now. Write down, try to find the domain for r and the domain for theta that would give you this semicircle here. And write down the double integral in polar coordinates. And if you become a little bit like Dr. Warren, maybe a little cocky, you're like, okay, I got this, Dr. Warren, then substitute for your x and y. Substitute for your x and y in your space sheet and try to do the rest of the problem. Try to at least do the rest of the problem. Try to make it all polar. When's your WebAssign due? When's your WebAssign due? When did I make that due? Did I make it due Thursday or Friday? Did I make it due Thursday or Friday? Friday, okay. Friday at 11:59. Okay, let me try to get caught up. You guys help me out. What do you think R is running between? What do you think R is running between? The radial variable. What do you think it's running between? 0 and 2. My radial variable is always running between 0 and 2, irregardless of where I'm at. What do you think theta is running between? What do you think theta is running between?
Negative pi over 2 and pi over 2.
Good, Red. Negative pi over 2 to pi over 2. Negative pi over 2 to pi over 2. Okay, so let's set up our double integral. This integral would be the same thing. This integral, my two-dimensional integral by Fubini, can be traded for two one-dimensional integrals. The outer integral is running between
0 and the square root of 4 minus also.
No, not quite, Michael. We're trying to avoid all the x's and y's. Theta's running between, you guys just told me, theta's running between, very good, Raylan, negative pi over 2 to pi over 2. R is running between, and you guys told me that too. Theta was running between there and there. R is running between
0 and 2.
0 and 2. Your space sheet, right now, we'll keep it as x squared minus y squared. If you guys forget one thing, I'm gonna jump up and down and throw my body on the floor. What's the differential become?
R.
R.
dr.
dr.
d theta.
d theta. Okay, we've got a confused little integral. It doesn't know whether it wants to be polar or Cartesian. Make it all polar. Make it all polar now. Make it all polar. You're doing your homework. You're doing your homework. All right, guys, how many people got to here? How many people got to here? How many people got to there? Now, this is where you're going to have to use some cleverness. What do you notice that you can factor out of both of these? What do you notice that you can factor out of both of those?
Negative r squared.
A negative r squared. What are you left with on the inside once you pull out that minus r squared?
Cosine squared theta plus sine squared theta over 1.
Very good. Very, very good, Jake. And what is cosine squared plus sine squared, guys? What is cosine squared plus sine squared? 1. So let's take advantage of that. And so now we're down to here. Now we're down to here. The inner integrals with respect to r. The inner integrals with respect to r. You're trying to integrate e to the minus r squared r dr. What integration technique would you use? What integration technique would you use to try to integrate that, guys? If you were facing this in Math 236, the integral of e to the minus x squared x dx, what integration technique might you use to try to attack that? U sub. What would you let your u be equal to? What would you let your u be equal to, guys? What would you let your u be equal to?
R squared.
Very good. Minus r squared. Minus r squared. Okay, we're abandoning this problem now. We're abandoning this problem now. How many people feel like they've got a shot? How many people feel they've got a shot for this homework problem? How many people feel like they have a shot? Rachel, you think you could finish this maybe? How about you, Luke? Do you think you could finish that? Kind of. I believe you can, Luke. I believe you can. How about you, Jake? You think you can finish that? Okay. So there, we've at least started problem 11 for you. We've at least started problem 11 for you. Do you want to work on another one? Do you want to work on another one? Do you guys want to work on another one? Okay, here's your homework. It's a flipped classroom. Which one do you want to work on now? Which one do you want to work on now? Given that we've got like a half hour. We've got a half hour. Which problem do you guys want to work on now? Whoever says the first one, that's the one we're doing. Well, you guys have control.
29.
29. Michael says let's do 29. Okay, so let's look at 29. I actually brought my book. Oh boy. Okay, write this down. Write this down. It's the same space sheet. Okay, this is a little bit more involved. Okay. It's a type 1 integral. It's written as a type 1 integral. X is running between 0 and 2. So your outside integral is 0 to 2. Your inside integral, where your g of x and your h of x, it's running from g of x equals 0, and the upper function is h of x equals the square root, all of this is inside the square root, 4 minus x squared. It's the same space sheet. It's e to the minus x squared minus y squared, and then it's dy dx, then it's dy dx. So write that down, write that down. How many people have this? How many people have this? Okay, these problems are harder. It's clearly harder. It's problem 29. It's not problem 11. It's problem 29. If you're going to figure this out, you're going to have to figure out what the domain D looks like. Okay, so give yourself a xy. Give yourself an xy. Now remember what a type 1 integral looks like. You've got a function g of x, you've got a function h of x, and you've got an a and a b on the x-axis. Who's the a and the b? Look at the limits of integration. Who's the a and the b? And let's at least get that on there. Who's the a and the b? Look at this integral. Who's the a and the b as far as the x is concerned?
0 and 2.
So let's mark that down here. I know my functions. I'm going to be using x's between 0 and 2. Now let's look at the bottom function. Who's in the position of g of x? Who's in the position of g of x?
0.
0. It's g of x equals 0, or y equals g of x equals 0, which is just that there, which is just that. There's the bottom part. There's the bottom part. The upper part, who's the h of x? Who's the h of x?
Square root of 4 minus x squared.
Okay, so now write down y equals the square root of 4 minus x squared, and try to see if you can't find out what this d might look like. That's the information you got. You try to figure out what d might look like. You know x is running between 0 and 2. Y is running between 0 and the square root of 4 minus x squared. How many people feel like they have a region? How many people feel like they have some sense of what the region looks like? If you feel like you got it, go to grid view. Go to grid view, guys. Go to grid view and hold up what you have. Hold up what you think that region looks like. Hold up what you think that region looks like. Yep. Everybody's right. Everybody's right. Everybody's right. How many a quarter circle? You guys saw a quarter circle there. Now again, I'll help us since it's homework. This means y is equal to the square root of 4 minus x squared, or y squared is equal to 4 minus x squared, or x squared plus y squared equals 4, which is your circle of radius 2. Now, you're only using the upper half of the circle as a function of x, and you're going between 0 and 2. Does this domain look, I'm going to use a vocab word that I never would use except I'm trying to sound smart. Amenable. Does this look amenable to polar coordinates? Does this look amenable to polar coordinates? Okay. You've got to find ranges for your radial variable, and you've got to find ranges for your angular variable theta. Try to figure out what r is running between and what theta is running between, and then write down the double integral. Write down the double integral that they're really looking for you to solve in polar coordinates for this problem number 29. I forgot you guys were here. Okay, let me see your double integrals. Let me see your double integrals. Let me see what you guys have for your double integrals. Hold up your double integrals. Good, 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 Jake. Yep, exactly right. Exactly right. Michael, I'm not quite able to see yours. Drop it down a little bit, Michael. Just lower it a little bit. Ah, shoot, it's still a little fuzzy. Let me see there, Emily. What do you got there? Good, Emily. Good, good, good. Cosmo, that looks great. Awesome, awesome, Luke. Awesome, Luke. Okay, okay. I see lots of good things. I think lots of good things. Theta's running between, theta's running between, theta's running between, the angular variable is running between
0 and pi over 2.
0 and pi over 2. Your angular variable is running between, 0 and 2. And guys, let me just point this out now. So many kids struggle with this, and they're going to be like, wait, how did the 0 and 2? And guys, you're going to have to fix it. They're going to be like, how did the 0 and 2 move inside the integral? And I'm like, guys, no. This 0 and 2 is with respect to, this 0 and 2 is with respect to x. It didn't move inside the integral. This 0 and 2 is with respect to r. They're two different things. Now the dx, the dy dx is going to turn into a what, guys? The dy dx is going to turn into a what? The dy dx is going to turn into a what?
R dr d theta.
R dr d theta. R dr d theta. Okay, now we're gonna abandon this problem. We're gonna abandon this problem. Where you see an x, and a lot of you guys had already started. Where you see an x, you're gonna put a. Where you see the x in your confused little integral. Where you see the x, you're gonna put a r cosine theta. Where you see an r, you're gonna put an r sine theta. You're gonna again use a u substitution to knock out the rest of this integral. Okay, okay. Write down this integral. You may need it for your homework. Not for this problem, but write down this integral because a lot of you guys forgot it. The integral, we're doing an indefinite integral. This is math 236. Math 236. The integral of cosine squared x dx. The integral of cosine squared x dx is equal to 1/2 x plus 1/2 sine x cosine x plus c. 1/2 x plus 1/2 sine x cosine x plus c. That might be useful in this homework. That might be useful, not on this problem. Okay, one more, and then we're killing class. One more, and then we're killing class. What other problem might you want help with as you're heading into WebAssign? What other of your homework problems might you want help with as you're heading into WebAssign?
19.
19. Okay, you guys with me? 19, and then we're done, okay? So let me read number 19. Number 19 says, use polar coordinates to find the volume of the solid underneath the paraboloid, holy crap, defined by z equals x squared plus y squared. And above the disk in the xy plane, defined by x squared plus y squared is less than or equal to 25. So you're trying to find the volume under the space sheet, x squared plus y squared, on a disk. So you got this paraboloid here, and you're trying to find the volume in between there and there. And the disk is described by x squared plus y squared. X squared plus y squared is less than or equal to 25. Is less than or equal to 25. Does this problem seem amenable to polar coordinates? Try to write down a double integral in polar coordinates that would find the volume underneath the paraboloid x squared plus y squared, z equals x squared plus y squared, over the domain D of the disk x squared plus y squared equals 25.
Dr. One,
Yep.
you just said equals 25, or is it less than or equal to 25?
It's going to be the whole domain here, Jake. It's going to be everybody down on that circle, everybody from 0 all the way out to. So that's why they have the less than or equal to there.
Gotcha, okay, thanks for clarifying.
And if you feel like you got your double integral set up right, if you feel like you got it set up right, then do the problem. If you feel like you actually have the right double integral, then go after it. And if you don't, then just hold off. I'll help you set it up here in just a minute. But if you feel like you got it set up right, go after it. Okay, stop wherever you're at, stop wherever you're at. Let's just get everybody on the same page. How many people recognize this as being a disk? How many people recognize, if it's equal, how many people recognize that as being a circle? If it's x squared plus y squared equals this, we got a circle of radius 5, and less than or equal to all the xy's that satisfy this is going to be that disk there. That is definitely not a function. This outer boundary is definitely not a function of x or a function of y. It fails the vertical line test for x. It fails what would be the horizontal line test for y. But is it very, very nice in polar coordinates? Is it very, very nice in polar coordinates? If I'm thinking about a double integral, theta would be running between where and where. If we're thinking about all the points r theta, we want all the points where theta is running between
0 and 2 pi.
perfect 0 and 2 pi. My radial variable is running between 0 and 5. My space sheet is who? Who are we integrating under?
X squared plus y squared.
The x squared plus y squared, my paraboloid. And what's our differential in polar coordinates? What's the form of our differential in polar coordinates? What is it?
R dr.
R d theta. Okay, now we got our confused little integral where we see the x, we're going to put a
R cosine.
r cosine theta, where we see a y, we're going to put an r sine theta. Can anybody automatically see what's going to happen with that? What's that going to reduce to? As I try to get you ready for the quest, what's that going to reduce to?
R squared.
R squared. I mean, you can put it in. You're going to get an r squared cosine squared theta, r squared sine squared theta, which is r squared cosine squared theta plus sine squared theta, which is just r squared times 1, which is just r squared. Look at the remaining integral. Is that a hard integral to do, guys? Look at the remaining integral. Is that a hard integral to do? So as miserable as polar coordinates are to derive, the book sets some pretty reasonable ones to try to attack. You don't need a lot of your integration techniques from Math 236. Okay, how many people feel like they have more of a shot for this? Raise your hand. Okay, I guess I lied. For the last time, stand up. For the last time in Math 237, stand up. Stretch. Okay, now let's sit back down. Okay. Your quest is when? Monday. What time? 8 a.m. Okay, it will not take an hour. I'll be a little surprised if it takes 45 minutes. I could probably do it in 10 minutes if I have to. Okay? There will probably be one justification. I'm not gonna change. Are you kidding me? You think my math is proof. I'm not gonna change. Chances are I'm not gonna put a proof on because that would just be too involved. Chances are I'll bury any of the theory in the max-min stuff. Will probably be buried in true-false questions. So when you're studying, be thinking, what kind of true-false question would I write if I was the teacher? Because who knows? You may be a math teacher. You may end up being a math professor one day. If I can do it, you can do it. Okay, all right, now, if you can turn on your cameras. I want to see all of your faces. If you can turn on your cameras. I want to see all of your faces. Okay, Now listen to me, listen to me. College can be an incredible time. It can be an incredible time. I mean, people look back on college and oftentimes they say it's the best times of their lives. And you're like, Dr. Warren, what the hell? I mean, seriously? Okay, and I get it, this semester in particular. But I just want to say, you know, there's 20,000 students at JMU. And they're all 18 to 22 mostly. And it still can be a very lonely place. There's a lot of students at JMU that are walking around this campus and they feel pretty lonely. There's a lot of students walking around the campus that have real adult problems going on. And I just want to put out there that once you're my student, you're always my student. I'm seeing you in Zoom right now, which is bizarre, instead of in here in the classroom where I can really see you face to face. But once you're my student, you're always my student. I'm looking out for you. I want what's best for you. I mean, I can't change your grade. I mean, ethically, I've got to decide what you actually know about Calc 3, leaving my class. But once you're my student, you're always my student. I don't want you walking around this campus lonely or in a dark place, feeling like you have no ear for somebody to hear you. Okay? You can always come to Route 108, which is my office. Okay? And listen, guys, I have been teaching since 1984 when you were -16 or 17. I have heard literally everything on that futon from students. Everything. Other than, Dr. Warren, I killed somebody last night. That I have not heard. But almost every other crime I have heard. Almost every other crime. I got caught DWI. I got caught drunk in public. I'm pregnant. I got caught dealing. I mean, I have heard almost every other crime. Dr. Warren, I just don't know if I want to go on. I mean, so if you come, I don't have advice. I don't have advice. I've got scars. I can show you all kinds. I got divorced. I've got having 3 kids live one place and 2 kids live another place. I've got all kinds of scars. But oftentimes, just talking is enough for people to start moving out of that darkness just by explaining. So you promise me that you will always come and see me, okay? You promise me that. I want to hear it. I want to hear it. I want to hear it. Say, I promise.
Promise.
Say, I promise. Okay, okay. Now I'm holding you to that. I'm holding you to that. Okay, I will see you guys on Monday. You're coming to the Zoom classroom. The final's going to be in classroom Zoom. You got to have your camera on. You got to have your mic on. And I got to see your little piano hands. And I got to see the piano. And I got to see the piano. I got to see those keys. All right. Thanks for playing with me this semester, this crazy semester. Thanks for doing it, guys. Appreciate you. Bye-bye.
Thank you, everyone.
Thank you, Dr. Warren.
See you guys.
Great.
See you, Michael.
Your last name, brother?
My students. I wish them best. Wish them the best.